Hello and welcome. I've been asked to do a video about transformers by my students. So it's going to be a relatively basic run through of how a transformer works, how it operates and functions. Transformers work on something called induction or electromagnetic induction, and this law was described by Faraday many years ago, where if you imagine this red pen here, if you can see that, that's a conductor, and imagine this bic. The bic is a magnet, yeah. All the time there's no relative motion between the bic and the red pen, no current will flow in this conductor here. But if I move the magnetic field relative to the conductor, or I move the conductor, current will begin to flow in the conductor. And you could imagine also that if I move the magnetic field towards the conductor, the current will flow in one direction. When I move it away, the current will flow in the other direction. And then we've got, of course, AC, that's current flowing in one direction and then the other. And transformers only work on AC. Faraday's law is given mathematically as the voltage induced across a coil is equal to B, which is the flux density, beta, the length of the conductor, sorry my L's a bit funny there, that's the amount of conductor that's exposed to the magnetic flux, and velocity, which is the rate of change of magnetic flux linking both the coils. So in a transformer, basic construction of a transformer, this is probably the simplest one that I could do. You normally have some type of core. In this case it's going to be a steel core, a laminated steel core, and wrapped around one part of the core we've got the primary coil, and the other part we've got the secondary coil here. And that's kind of all you need for a transformer to really work. Another thing to note with a transformer is that the power in is equal to the power out, and power is equal to volts times current, and that's quite an important relationship between the two. So how does it work? We're going to relate back to Faraday's law. Here we've got a primary coil. Now if we feed this primary coil with an AC input, what will happen is the coil will form a magnetic field, and that magnetic field is strengthened by the steel core. The magnetic field will rise and fall because remember it's AC, so we've got a magnetic field that will rise and fall with the current flowing through the coil. Now remember what I said about magnetic fields. If you've got a magnetic field that's moving in relation to a conductor, it will cause a current to flow through that conductor. And that's what happens here. The core is a conductor, of course, so the rising and falling magnetic field caused by the AC input induces a current into the conductor, which flows both ways, like AC. And of course this creates its own magnetic field. The core will create its own magnetic field, and that magnetic field will also be rising and falling. And because that magnetic field then comes into contact with the secondary coil, it will induce a voltage into the secondary coil. When we come back to Faraday's law, the voltage induced is equal to the strength of the flux density, the length of the conductor, and the rate of change of flux linking both coils. But of course the flux density is mutually shared by both coils, and the rate of change is the same. Therefore the only difference on a transformer is the length of conductor that's exposed to the rising and falling flux. Therefore that's why with a transformer, to know what its output or input voltage, to know what its output voltage is going to be, all you really need to know is the ratio of the coils. For example, if we had a primary, hope you can see this by the way, if we had a primary with a coil ratio, that's the ratio of turns in the coil of 10:1, then if the primary had a 240 volt input, The secondary would have a 24 volt output. Because the power in is equal to the power out, imagine the primary drew 10 amps, for example. Then the secondary would draw 100 amps. And the more we reduce the secondary voltage, the more current we can produce in the secondary. And one of my students is making a spot welder for his project, and he's going to have a very, very low turns ratio. He's looking to produce something like 800 amps on the secondary, which means, of course, you're going to have to step this voltage down quite some way. So as far as transformers are concerned, that's how they work. There's not really a lot more to them in terms of what I would explain here. The reason for the laminated steel core is because with the transformer, the currents which are flowing through the transformer will actually cause power loss. So the laminations stop this phenomenon called eddy currents flowing across the surface of the core, causing power loss. And transformers are probably one of the most efficient machines, the most efficient machine we have. They're about 98% efficient usually, something like that, 98%. And also for George here, if we look at our transformer, we've got thin coils here and thick coils there. So in a transformer that's got a massive step down, because the current potentially could be very, very large, you would need to make sure that the thickness of the wire was able to rate it to take that amount of current. You can't just go around creating step down transformers with different wire thicknesses which can't handle the current. So that's quite an important point. Another point with transformers is quite often they're arranged so we can split the primary and secondary coils to achieve different voltages on the output, and that's called tapping. So sometimes you can split the input and just use part of the coil there, and the same for the output as well. And I think as far as that goes, for just a basic primer on transformers, that's kind of all I need really to do today. If you've got any questions, just get in touch. Bye bye.